Partial fractions part 5, the equating coefficients method. Example 5. So again, a fully factorized denominator using these factors to write our partial fractions, and then we want the same common denominator, x minus 3 into x plus 1, like this. So if the denominators are the same, the numerators must also be the same, and up to this stage the equating coefficients method and the old one that we've seen, the substitution method, are exactly the same, and making the numerators equal to each other, that's still the same for both methods. But from here onwards what we're going to do is expand the brackets on the right hand side, so we've got ax plus a plus bx minus 3b, and then collect like terms. We have x terms here and here, and we have constants here. Now on the left hand side we have 6x minus 2, so we can see that the coefficient of x is 6. The coefficient of x is 6. So a plus b is equal to 6. That's looking at the x terms. Now when we look at the constants, we have a minus 3b, which is equal to the constant here, minus 2. Now we have simultaneous equations. So I've changed the signs throughout. It's like multiplying both sides of the equation with minus 1. Now what I'm going to do is add this equation to this one. That's got a, that one's got minus a, so they will cancel. So adding them, the a's cancel, the b plus 3b is 4b, 6 plus the 2 is 8, so b is equal to 2. Then we can solve to work out what a is equal to. If we substitute 2 into this equation, so a is 4. And then we substitute those values in, and we've got our partial fractions. A is 4, b is 2. For simple partial fractions, this is a good method, the equating coefficients method. But if you have like 3 partial fractions, you can have a lot of algebra all over the place, and I think it's slightly easier to make a mistake using this method, and the substitution method is better.